introduce these horrible analytic objects. Dave Cavalli said this morning in the verse that just the name makes his stomach churn. And not because Dave is a topologist. Then this perhaps makes the analysis of like a churn, which is a transverse co-cycle, that's purely combinatorial. And my last slide yesterday was that actually these two things, which seem to be very different, are actually the same thing. So first, the combinatorial objects are easy to determine. Okay, that's a vector space, and you can compute the dimension very easily. And but the theorem is that you have this natural correspondence between both things. So the map is just the obvious map, namely that given a transverse Hölder distribution, namely a horrible analytic object, you associate to it a transverse co-cycle just by to each arc you associate the function associated to the constant function, the number associated to the constant function 1. Oh, okay. That's essentially that's the easiest thing you can think of. And I'd like to say a few things about how you prove this, because actually it's also analytically interesting. And the key point is that gap formula, gap lemma. And what that says is the following. You take the horrible analytic object and you can express it in a relatively explicit form. The formula is bad. Don't try to completely understand what it means. But what it says is the following. So I have an arc which is transverse to the lamination, and I have a Hölder continuous function phi, which is defined over this arc, and my transverse distribution is going to associate to that arc a number. And the way you can compute the number is by this formula here. And the key points are the following. Is that the key ingredients are, first of all, it's a sum over all the components of the complement of the intersection, all the gaps between the leaves. That's why it's called the gap lemma. Okay? So it's a sum over all these gaps of terms which are the term which is alpha of a certain arc, namely that something which is completely determined by the transverse co-cycle. And what this arc is that first of all, you choose once for all an orientation for the arc. Pick the one you want, and then for every gap, you take the sub-arc which goes from the negative endpoint here to somewhere here. You stop wherever you want. Okay? KD, that's an arc showing the negative endpoint somewhere in D. And so that's something which is given to you by the transverse co-cycle. And then you take this, which is how much phi jumps out of the gap. These 2 points are the endpoints of the arc, and you take the value of phi here, and you subtract the value of phi there. Okay, and then this term is similar here, except it corresponds to this endpoint here. So what's important in this formula is that on the left side, you have the transverse distribution, and on the right side, you have something which depends only on the values of phi at certain points and on the transverse co-cycle. Okay? So that's how you establish the one-to-one correspondence, because it shows you that once you know the transverse co-cycle, then you completely know the distribution. And then conversely, if you are given the transverse co-cycle, then you can use this formula to construct by hand a transverse distribution. Now, so in this way, you can go back and forth between the analysis and the combinatories. I would like to draw your attention to, you have to check a few things. For instance, it's unclear why it should not depend on the orientation. See, if you reverse the orientation, well, this point here gets replaced by this one, so this term gets replaced by something else. And also here, the signs become different, and you have different arcs too. So you have to check that this does not depend on the orientation, for instance, and things like that. But it's not. It's not so important.
But since you have all these arcs, suppose you sort of randomly change the orientations of each of these arcs.
Then you have to check that it's invariant under homotopy of transverse arcs also. It's not difficult. It's not. A remark is that this formula, I mean, this formula seems to be interesting even when alpha is just a transversal measure. I mean, one of these objects which people have been studying for a long time. And in particular, the point here is that if you have a transverse measure, then the left-hand side makes sense, even if phi is just continuous. So you would think that perhaps it's hard for every continuous function. When you think of that, and then you remember when you learned about, you go back to your graduate real analysis class, and you remember these functions which are non-constant, these functions on counter set, on the real line, which are constant on the component of the counter set, but which are non-constant. Well, if you take such a function, then the jump at the gaps here are all 0. So that would tell you, on the other hand, you would have a problem with the. So what does it say in this case? Well, that doesn't work for such a function. Okay. So that's the key ingredient. And what's the key ingredient in the proof of this one? Why does it work? Well, I think the main one is this one's property of Hilbert distributions. Which is the following, is that, in general, when you have a distribution, you have something called its support. Why define it as you want. But in general, to evaluate a function, if you evaluate a distribution of the function, not only do you need to know the function of the support, but you need a little more. Well, not for a measure. Measure, to define the integral, you only need to know the values of the function on the support of the measure. Well, we have exactly the same property for Hilbert distributions. It's now it is undergraduate real analysis. So it's not just a few epsilon. It's very easy once I give you the statement. You can go home and try to prove by yourself. It's very simple. So what that says is that, well, if you want to determine alpha of phi, well, you need to know the restriction of alpha to the support, the restriction of phi to the support of alpha, which in this case is intersect with lamination. And then the second point is that that restriction here is completely determined by the jump at the gaps. Well, why is that? It's because you know that, but this property is true only if phi is Hilbert continuous. Why is that? It's because essentially this set here has Hilbert dimension 0. We saw that yesterday. And phi is Hilbert continuous. Okay, now what that implies is that phi of that the image has Hilbert dimension 0 in R. And in particular, it has 0 length. And if it has 0 length, well, when I move from the point X to the point xk, well, I can see how much I jump. But if the green set has 0 length, then I don't jump any significant way there. So the only good jump is the only thing where I really jump are over the gaps. So because of that, you have this formula here that the difference between the value of the function at this point and the value of the function at that point is the sum of the jumps over the gaps. And this begins to look very much like this formula here. And indeed, if you, once you have these, you formally put an integral sign pretending that everything is a measure. And you notice that this is a sum only on the gaps t, which are between x and this endpoint here. And formally, you get this. That's what it comes from. Okay, and then the last step is that, that's what you do if you're a physicist. If you're a mathematician, you may want to justify a little bit the computation. And in particular, you might want to justify that the series here is convergent. And it's not an unreasonable idea the log of the length grows roughly like log n. Okay. So when you take this sum here, which is the second term, that's really the one which is analytically harder sum, which is called no problem. Okay, in this sum, well, you look at this term here. Because the function is Hilbert continuous, well, it's the same as the distance between 2 points times power u. Okay? And so this, and the length, the distance between these 2 points here, that's the length of the corresponding gap. And because of this estimate here, it's on the order of some exponential to the power n. It will even decreases exponentially. And so that gives you that this term here also decreases exponentially. And on the other hand, we have to work a little bit here. For the other measure, this will be uniformly bounded. But here, unfortunately, because you have pluses and minuses, if you keep taking a combination of plus and minus, that can go to infinity. However, by understanding the combinatorics, you see that it goes, you can show that it goes at most linearly. So you have something which may go to infinity, but at most linearly, times something which decreases exponentially, so converges fine. And so what I showed you is that this term here makes sense, but also all the formula, with that you can justify all the formal computations without any problem. It's not, essentially, that's the whole proof. I mean, there is no additional estimates needed. Okay, so in this way, we have established this one-to-one correspondence between combinatorial objects and analytic objects. And that's where I planned to finish my talk yesterday. I'm a little behind. And the question is, why should we care? And actually, why should I care? I mean, what's always good with this kind of conferences is that there are some people here who seem to like very much the analytic part of the Hilbert distribution aspect. Okay, and then there is Dave. Well, with so much churns when that's the other culture. And unfortunately, you know, I've been working with Dave for a long time. I behave like Dave. I mean, I come from that school. I like combinatorial things. So why should we do that? And so that's what the second part of the talk is about. And it's about the space of measured geodesic laminations from the topological point of view. So that's the space where the combinatorial stuff comes from. Okay, so this is an idea which goes back, which was introduced by Person. I mean, this whole idea is that, okay, for ages, the topologists have been interested in this thing here, which is you take a surface, negative or negative thing to make it more interesting, and you want to understand the space of the set of simple closed curves on the surface modulo deformation. You know, low-dimensional topologists love this thing. And the problem is this here, deformations. That's clumsy. And so the trick to get rid of the deformations is that you endow, you turn the picture into this here. Instead of the topologist would write this surface with a big hole, not just like a nice cusp like that. But you turn the picture into this here, and then you put a hyperbolic metric with a finite area or whatever. Because, and then there is a fact, which is that essentially every simple closed curve can be deformed to a closed geodesic. Now there are a few for which it doesn't work. The ones which you can trick to a point, and that's only one class. And also there are the ones which escape to the cusp. But that's only finite element classes too, so you only use finite element those. Forget about those. Right? So in this way, what you gain is that you establish a one-to-one correspondence between the deformation classes of simple closed curves and simple closed geodesic with no equivalence class here, no deformations. Okay, that's the great idea from the topological point of view. You have to worry about deformations. And then you go one step further, in that to understand the set of simple flows, you can say, hey, that's a geodesic lamination. So, so you could consider the space of, so this set here, you have a natural injection in the space of geodesic laminations here. And so you think, hey, perhaps if I want to take, the whole idea is to be able to take limits in this set here. Then we take limits here. And then this space here actually is a topological space because every geodesic lamination is a closed subset of S, and you remember from your concept topology class perhaps that on if you have a metric space, consider the space of bounded closed subset of that space. There is a natural metric, that's the Hausdorff metric. You know, the ones where you consider distance, those where you identify two spaces if you cannot distinguish them if you're nearsighted. And okay, so you have that space which is standard, and you can show that it's a closed subset of the space of all the closed the space of geodesic laminations is a closed subset of the space of all closed subsets, and so the upshot here is that this is compact. So you have a sequence of curves, we're going to take the limits. That looks like a nice idea. The only drawback, if you do that, is that this space here is totally discontinuous. Well, you can show it by hand, but I can advertise perhaps the recent result of myself and my students here at home, where we say that you can compute the Hausdorff dimension of that metric. That's not the same result as the result of Biermann series, which I mentioned yesterday. Although the proof is very closely related. So that space here has Hausdorff dimension 0. So in particular, it's totally discontinuous. And then, okay, for an analyst, that's no problem. But for a topologist, topologists don't like Cantor sets. We like manifolds. And so that's not good. So, in other words, you have to try something else. You want real numbers. And to introduce real numbers, the idea is to put transverse measures. Well, because I said that a closed geodesic, that if you can consider it as a geodesic lamination, but also it has a natural transverse measure. And the way you do that is just the counting measure, the Dirac measure. So you have a closed geodesic, like this, and then you take a transverse arc, and then for every subset of the arc, you count how many times the subset intersects the closed geodesic. Okay, that's a standard transverse measure. And in this way, what you have done is to embed the space, the space I was including in the space of simple closed curves S, is this space of measured geodesic lamination. So what's a measured geodesic lamination? It consists of two things. First, a geodesic lamination, and then in addition, you fix a transverse measure on it. You want it to have full support. So that there is no RPC. And what this implies in particular is that the geodesic lamination cannot have an isolated leaf. If you have any isolated leaf, you cannot go into cusps. Okay, that's a minor thing. And then, so here that looks bad because not only you're considering families of geodesic laminations, but also you have transverse measures and everything changes. So, but you can put a topology on that. But I think I don't want to waste too much time. You can just briefly read, but intuitively, there are many ways of defining the topology. But the good thing is that I always give you the same one. Okay, one simple one is that you can say that the arc is generic if it intersects transversely every simple geodesic. Now, it doesn't seem that it would exist, but you remember that this result of Biermann series, which I mentioned yesterday, says that there are very few simple geodesics. They only form a set of Hausdorff dimension, their union only forms a set of Hausdorff dimension 1. So there are so few of them that actually any arc can be approximated by a generic arc. And for instance, almost every geodesic arc, you take one at random, then it will be generic in this sense. Well, if you have an arc like this, and it's transverse to all the geodesic laminations, then each geodesic lamination gives each measure of geodesic laminations gives a measure on that arc. So, and then what you can do is that you can topologize this set by the weak start topology on the set of measures induced on this arc. Well, what that means is that you need to say that the sequence of measured laminations converge to another measured lamination if and only if for every generic arc K and every continuous function defined on that arc, then the integral of phi with respect to the transverse measure with respect to the measure alpha m converges to the integral with respect to the transverse measure of alpha. If you think of it, it's a fairly natural topology. I'm not an analyst, I don't know. I hardly know the general definition of this star. And okay, then you have a simple result which says that if you put that topology, then the ones coming from a simple closed curve, okay, when you have a simple closed curve, I begin to read the geodesic lamination with the transverse measure, and then you can multiply the transverse measure by whatever number you want, and the result says that the ones you obtain that way are dense. So I said it's like this idea of going from the set of simple closed curves to the space of measure lamination. You have to think of it as analogous to the process on which you go from Zn to Rn. And really, if you're a topologist, the reason why you should be interested in that is really to understand a little bit what happens at the in that set. And that's, if you think about why you want to consider real numbers if you study Zn, very often it's because you want to go to infinity in Zn. Right? I don't know about that. People might even make a mistake, but that's a by view of the thing. And here it's the same. Same idea. Okay. But really, what the topology is finding?
You say that the space of lamination is totally discontinuous. And you said we introduce topology of the measured lamination.
Yes.
Is it at this level already obvious that it contains arcs?
What is this example? Yes. Yes, that next slide, it's a manifold.
Yeah, is it obvious? Contains curves?
Which set?
This set, ML.
ML. No, I don't think it's.
These contain rays.
Contain rays, yes. Yeah, no, that's it. No, you have to. I don't think so. I mean, no, the first time you see the definition, you might think it's a couple sets too. There is a problem with the word obvious, but for people like me, sometimes it will not be obvious. Okay, but actually, the nagging point in this space is that, okay, we're going to see it, okay, if you look at this last line, it's a topological manifold. So it's homomorphic to some Rn, which is in that way. However, it's not a smooth, so it's not a differentiable manifold. And that's really why I started getting interested in these weird objects. Okay, because it's a piecewise linear manifold. So first, what Thurston showed that Thurston answered Etienne's question in the sense that he computed the topology of that tree. And the idea is that the first idea, which is relatively natural, is that if you look at enough generic arcs, then this to completely determine the measure lamination. That's quite believable. So you can find n arcs so that if you evaluate if you integrate this R to effect to the transverse measure, I give you a map from the space of measure laminations to Rn, one copy for each arc. And the fact that it's an embedding is natural. But what's more surprising is that you can determine the image, and that the image is a piecewise linear submanifold of Rn. Now, what's piecewise linear? I have to remind you a little bit that the map is piecewise linear. There are many definitions, but one way to do that is to say that you can decompose the domain as a union of finitely closed polyhedra, and where the map is linear. And this one is continuous to be linear. Okay, and so piecewise linear submanifold, that's something where you have piecewise linear charts which make it look like RP in Rn. So you take the standard definition of manifold, but you replace of submanifold, but you replace differentiable by piecewise linear. And piecewise linear homomorphism instead of diffeomorphism. Okay. And then in addition, if you take an additional generic RK, then you can express this number here, alpha of k, namely the integral of the measure of that arc in terms of the other ones. And not only you can express it, actually it's a very explicit formula, which you can make explicit, and it's also piecewise linear. So what that says is that if you take two sets of arcs like this, then the change of chart is also going to be piecewise linear. So because of that, what you get is a piecewise linear, is a structure of a piecewise linear submanifold on this space here. So you have to understand what that means. That means that this is a topological space, and you have charts which model that space over Rn for some dimension n, and but the change of charts are piecewise linear and not differentiable for differentiable manifold. And then something which is not too important here is that person was also able to completely determine the topology of this space, and it's just some Rn where n is this thing here, 3 times the exact characteristic of the surface minus the number of curves. I mean, the formula is not important. It's not even important. For the talks, this is not. What? Trying back. That means you are the closing lemma. That means you approximate geodesics by things which are almost geodesic. And you put explicit coordinates in that. Okay, now, piecewise linear manifolds, they've been around in topology for a long time. Right? It's a nice way to interpolate between topological manifolds and differentiable manifolds. I should say one thing, that you can show that, okay, you will think that it's a problem with the method, that this is wrong. But actually, you can show by hand that you cannot put on this space a differentiable structure for which, on this space here, you have natural action of the group, namely the group of diffeomorphism of the surface. Right? So any structure, any structure I want to consider here will be invariant of that. And you can show that there is no differentiable structure on this space which would be preserved by the action of the group of diffeomorphism. In other words, that you cannot conjugate, well, exactly that, yes. So really the piecewise linear context is the only one which is available to you. And the problem is that, on the other hand, people like to do calculus, and calculus for piecewise linear manifolds, I'm ahead of myself, calculus for piecewise linear manifold, that's a bit annoying. So I'm going to take an example, which is that everything you do for simple closed curves, you can often extend it to measure laminations. In particular, many functions have this property. One of them the length function. Like, it's a simple one, so I'm going to choose this one as a guide. Okay? So the length function, if you have a closed curve and a hyperbolic, then you consider the length of the closed curve. But if you want it to be invariant on the formation, what you do, you take all possible closed curves which are notable to that curve. You take the length of those, and you take the infinite. Well, in practice, what that means is that it's just I told you that this curve is homotopy to a unique closed regime. You take the length of that one. Okay. And so it's an observation of first term that you can extend it to a continuous function, which is linear in the sense that if you multiply the transverse measure by a number A, then you multiply the length by the same number. Okay. Let me show you how you do that. It's a simple idea. You have the geodesic lamination bag, but you can take fundamentally transverse arcs so that which cut the leaf into compact leaves. Okay, you can always do that by way to answer. Okay? So now you have compact arcs. Well, for each arc, you can measure its length, and then you integrate the length with respect to the transverse measure, and then you take the sum. You take the sum over all the boxes. So it's a natural idea. You see again, the key point is that you take the length of this arc and you integrate with respect to the transverse measure. And then the continuity, once you understand that, if you vary the measured lamination, where the length of this arc varies continuously and you vary the measure varies continuously too, so the length should vary continuously. That's not the proof, but that's the idea. So it's continuous. But the question is it differentiable? And so the problem that what's the differential? Now you remember that when you have a differentiable manifold, the differential is a map or tangent map. It's a map from the tangent space of the manifold now you go into R, so it's going into R. And so the differential should be a map like this. But the problem is that this is not a differentiable manifold, it's piecewise linear. So what's the tangent space on a piecewise linear manifold? You know, like a polyhedron, what's the tangent space on at a vertex? Well, there is a notion of tangent. There is a notion of tangent vector. Just take the usual definition for differentiable manifold, and then you translate it to the piecewise linear complex. Okay, so I don't know. You take you standard textbook in differential geometry, and you see the definition of tangent vector we use there. So there are various ways of defining tangent vectors on manifold. I don't think you can use derivations here, but okay. My favorite way of thinking of a tangent vector is as something which is tangent to as an equivalent class of curves. Namely, you say that so you have a point. To define a vector, you define an equivalent class of curves when you say that two curves. The two curves are equivalent if you have two curves at the point here, and you say that they're equivalent if they have the same tangent vector. That's what you're aiming at. So what you say that you consider their images under a chart, and you say that they're equivalent if their image here is tangent. And the point is that actually the key point is that this property is invariant of the chart if the change of chart is differentiable. But actually it's also invariant of the chart if the change of chart is piecewise linear. So actually this standard definition of tangent vectors in differentiable manifold extends to the piecewise linear context without changing anything. The only thing you lose is that a piecewise linear map is not linear. And so, in particular, the space of tangent vectors, which you can always define in this way, that's not a vector space. That's not necessarily a vector space. It doesn't even have a multiplication by -1. Because you know, if if you have curves here, which are tangents, where having the same tangent vector in one direction and in the other one, well, when you do the change of charge, they could look like this. Then you're not being aligned anymore. So you don't even have that nice operation. You do have the operation of multiplication by positive numbers, however. So that's a little inconvenient, but actually topologists have known how to work with these things for a long time. However, I'm trying to do some analysis here. I'm trying to differentiate. And so how can I do that? And you know, when you step on a problem, what you do is that you do examples. And so you can do a simple example by going back to, by taking one which is associated to an interval exchange map. So you remember, I told you yesterday that about interval exchange maps and how they give rise to geodesic laminations. And also I told you that the Lebesgue measure on the interval gives you a transverse measure for the geodesic lamination. So you can just take this one, which is one of these things. I never thought of this on the rotation of this one. Now everybody here talks to me about that this one is the rotation of this one. I agree with that. But, so it's a simple one. It's an interval exchange map on two intervals where you have one of length 1 and one of length t, and then you have this one here and this one there. And then when you construct the suspension, then with the freeway, remember, where you take a rectangle going from here to there, that gives you this fat rectangle here, and you have this teeny one here with t going this way corresponding to the other one. Okay, and the surface is a function for us. Well, it's something nice. And so what I'm going to do is I'm going to let t vary from 0 to epsilon. So I have a one parameter family of measured geodesic lamination, and then what I have is a curve in this space. Yeah. Alpha t, that defines a curve here. And you can actually show that this was in the curve. This was in the structure. And so, and then you do draw pictures. Now, I told you that for a generic interval exchange map, it's going to have infinitely many leaves. That's annoying. I don't know how to do counter sets. However, there is something nice, which is that if you take t equal 1 over n, I'm trying to have t goes to 0, so go to 0, so it's not about idea. Then it's simple because actually you just have all the orbits are parallel. And so, actually, for t equal 1 over n, what you get, the geodesic lamination is just a single closed geodesic. Here is for n equal 4. So, 1 of 1/4. That's just a single geodesic which goes once around the hole here, and then n times this way, and then goes back. So, go back here. On the other hand, the transverse measure is t. So, in this case, t corresponds to 1 over n. So the transverse measure is the counting measure. And you evaluate, let's take this arc here on the picture. So the intersection of this arc with the geodesic lamination at n points here, well, you call them x. So for later, you put all the odd ones on one side and the even ones on this side. It's going to be nicer. Okay? So you have n points like this. And the transverse measure is you evaluate the function at this endpoint, you take the sum, it's a finite sum, yeah? It's a Dirac measure. And then you divide by 1 over n. That corresponds to the t factor. Okay, now you just sit down the description of the orbits here, of the Lebesgue measure, and so on. That's what you get. That's relatively simple. And if you let n tend to infinity, when the picture converges to this here, then you have this geodesic here, which it turns n times. When if you let n goes to infinity, this geodesic is going to start turning infinitely many times, and in the limit what you get is one closed geodesic, and then a spiral like this. So that's what we saw yesterday. And then, if you look at the intersection with my arc here, I get infinitely many points which accumulate on the point of intersection with the closed geodesic. Okay. Now, you know what I'm trying to do? I'm trying to find, I want to find an interpretation for this derivative here. I have a curve, t gives alpha of t, and I want the tangent vector. The tangent vector formulae is d over dt of alpha t at t equals 0. And d over t plus because I only want the right derivative. Well, so then you go back to the definition of the derivative. The derivative, so now this is a family, these are a family of measures. So I'm going to plug in the function phi, defined for my arc k. I got it. So I'm going to take the derivative. I want to take the derivative of alpha t here with respect to the time t. And the definition of the derivative, well, that's alpha t of phi minus alpha t of 0 divided by t. Okay, that's calculus. And then since I don't understand all the t's, I'm just going to look at the ones that equal 1 over n. So, actually, you know what? This is more important. Yeah. Okay now? So I know the derivative. So alpha of t minus alpha of 0 divided by t. Well, for t equal 1 over n, I can do this. T being the n at the top. And then I go back to the definition of this. It's the Dirac measure. So I evaluate the function at these endpoints. And I have a 1 over n, which cancels out with this one. And then here I evaluate the function at this point. That was for t equals 0. And that n here gives me an n here. Now you see, I have infinity. I mean, when n goes to infinity, this goes to infinity because you have many, many more points. But this goes to infinity too. Infinity minus infinity, well, that's not 0 like my calculus students think, but it's, so that's not 0, that's just interesting. So you play a little bit and you incorporate these in here. And then, look, you're taking the sum from 1 to n of the value of the function here times the value of that other point there, times the value here. And my calculus students, they do know right away that if you let n go to infinity, you get this here. And I mean, the sum from 1 to n is the 1 of infinity, and just you plug in n equal infinity there too. And the point is that if you use this labeling, which is nice, to order your points, see that at level n you have x1, x2, x3, x4, depending on the n here. Well, when you go to infinity, you still have x1, x2, x3, x4, x5, and 6. And there is a way where the x3 point here is going to cover the x3 point there. So at least formally, we're not trying to prove anything here, but formally we find this here. That's a physicist proof. But we've seen this guy before. Yesterday there was an example of transverse distribution. You remember that? That's the example I gave. Yesterday I gave an example like this, where you take the sum of the infinite sum of the different value of phi between the value at the least point and the value at all the other points. Well, that's how I got started in this whole thing, just by staring at this example and drawing lots of pictures and so on. No, that's all right. So then that's the next theorem, which says that, okay, so that's only a very heuristic argument, but then you can justify it. And more generally, if you take any curve, if you take any curve in the space of measured lamination, and there is only one parameter family of curves, and which has a tangent vector for the piecewise linear structure, then for every hypercontinuous function defined on a generic arc, well, you have a number associated to each. You consider the integral of phi with respect to alpha t, and then you can take the derivative, and the derivative exists, and it also defines a Helder discontinuous for the Helder distribution for the norm on the Helder continuous function. So it defines a Helder distribution on that arc here. And then, in addition, as the transverse arc ranges over all generic arcs, then you can show that the support of this transverse distribution gives me a geodesic lamination, which usually is larger than the one the support of the measure lamination alpha 0. In this case, for t equals 0, I just have a closed geodesic, but when I come to the derivative, its support is a closed geodesic plus additional leaves. Okay. So the whole point here is that going from the combinatorics of this piecewise linear structure, you end up with an analytic object that gives an interpretation of a tangent vector as a geodesic lamination with a transverse Helder distribution. You've gone from the topology to the analysis, which is what's important here. And then there is a converse. This is what. Conversely, if you, well, you don't need to read everything here. I'm afraid the transparency is too full. But the idea is that, conversely, if you are given a point at in the space of measure lamination, if you're given a measure lamination and you're given something which looks like a tangent vector at that point, namely you're given a geodesic lamination which is larger than the support of that, and with the transverse Helder distribution, then you can characterize what if that geodesic with a transverse distribution will correspond to the tangent vector of the lamination. The conditions briefly are: the first one says that the support for the Helder distribution should not cross the support of alpha 0, and then the other two are a certain positivity condition. I don't want to. It's not important. It's just positive. It's just some positivity condition. And in particular, so that gives you a way to understand this tangent space in an analytic way, where starting from a measure lamination, so with a small support here, alpha 0, well, the tangent vector, you obtain it by adding these geodesic, by taking a geodesic lamination which is larger, by adding some isolated leaves, some minimal things. So what condition 2 says is that if you add a minimal sublamination, then it has to be disjoint from everything else. And on the other hand, if you add an isolated leaf, then as a corollary, it has to be its ends have to be asymptotic to the support of the measure lamination to start with. And now, if you fix such a delamination and you consider all possible transverse Helder distribution which can occur in this way, then they form a linear face in the space, in the tangent space, and which is not trivial only if the lamination is chain recurrent. Well, you don't know that is or you don't. It's not too important. Okay. Forget about this remark, I will talk about it. Okay, so the setup here is that
you're at the green point, and you preserve the green point by adding a small coefficient on the rest of it. Is that the idea?
Yes. Yes. You're going to add, you're going to end up with this is what if you Now, so what I did is to transform this point in your tangent vector, which is something very combinatorial, to something analytic. And so how can we use this? Well, I did say something got the proof here. It's a formally you can take a slide saying that every tangent vector gives you a geodesic lamination with a Handler distribution, with a transverse Handler distribution. Proving that formally it's an easy you can start with the gap formula, for instance, and then you do formal computation, it works fine. It's a little more tricky to justify. You need some broad estimates, which are not completely trivial, but you work hard, and once you've worked hard enough, then you're done. You don't have to think anymore. So for instance, let me go back to that idea of the length function. The length function was defined on the space of measure laminations. And so you want the differential of that. And you remember what I said, that the length function, you define it by taking the geodesic lamination, you cut it into small pieces in transverse arcs, you look at the length of each arc, and you integrate the transverse measure. Well, if I want to compute the differential of the length, well, what I need is a curve which is tangent to that tangent vector, to the tangent vector. Okay? So I take the tangent vector, I take a curve which is tangent to it. What is it? Did I say perfectly someone? I know I didn't say that. So, okay. You take a family T gives alpha T, which is with derivative of this vector, and I want to take the derivative of the length. Well, derivative of the length, that's derivative of that integral, I said. Well, everything is so natural at this point that the derivative of the length is just the length of the derivative. I mean, this makes sense. This integral makes sense even for the geodesic lamination, the transverse Handler distribution, because the length of this arc is actually a Handler. It's actually a Lipschitz function of the arc. So you can integrate it with respect to the transverse Handler distribution that splits out the number. Everything is so natural that when you take the limit on both sides, you get that. And it's linear. So actually, the derivative of the length of this length function, that's just the length function defined on the space of geodesic lamination transverse Handler distribution. So it's very natural in this context. Okay, before. As a preparation for next time, so that's exactly the kind of results I was aiming at when I started this program. And everything started just by looking at the example I gave you. The question here is the following. If you're a topologist, you don't like to have to fix a hyperbolic metric. I mean, what happens if, when I take a metric like this to study the space of simple closed curves, what happens if I take a different one? Okay? Well, then nothing changes. I mean, this theory is metric independent. And the reason, so, if I take another metric, then there is a standard fact about negative vector metric, is that for if I have a metric, a geodesic for the metric M, then there is I can associate to it in a unique way and geodesic for the metric M prime. That's the key word here is that something which is geodesic for the metric M is going to be quasi-geodesic for the metric M prime. Okay? So there is a unique M prime geodesic which is going to stay at one distance of G. Okay? So in this way, I give you a natural correspondence between geodesic here and geodesic there. Now, if you take two geodesics like this, which do not cross, and these ones are not going to cross either, and therefore you get a natural correspondence between M geodesic laminations and geodesic lamination for the other metric. Okay? So the theory of geodesic lamination, it's metric independent. Right? There are other ways of defining this, which make it a little more natural way. You never use the word metric anywhere. Now, the transverse measure, actually, that intuitively, it's a measure which is locally defined in the space of leads or visualization. Well, again, because of the correspondence, that gives you a translation between transverse measures for an M geodesic lamination and a transverse measure for the M prime geodesic lamination. So these measure lamination places also are the same. But then if you think a little bit about it, you can also that the correspondence preserves the piecewise linear metric. You have to work with them more. But this space here has a piecewise linear manifold, this is metric independent. So that's why really topologists are really pursuing that. And the important addendum is that this correspondence also is not only it's continuous, but it's hampered by continuous. So that's something which is actually fairly familiar to the people who do these kind of things. And for whatever metric you put on the space of geodesics, well, whatever distance you put on that space, I mean, whatever natural distance, then it respects this part here is Hammer continuous, and the inverse is also Hammer continuous. And so, what that shows you is that when I take geodesic lamination with Hunter distribution, transverse distributions, it's also metric independent. So actually, this whole theory, which was topological to begin with, is still topological at this point, meaning that this does not depend on the choice of the metric. Now, the analysts don't care about this kind of things, but the topologists do care, because we don't want the original problem studying deformation classes of simple closed curve. That is very metric independent. So you don't want a theory which at the end you depend on the metrics. But everything I did here, you can do it without considering any metrics. Okay, and then, so I think that's it for today. And then tomorrow, I'm going to, so here I chose a sample, the main function as an example. Tomorrow, I will choose, there are many more applications of these things, but I will choose one, talking about three-dimensional hyperbolic geometry, and how you can apply these techniques to that context. Okay, thank you.